code generators for architecture description languages that allow you to embed application-specific component behavior languages. So we come from a software language engineering group, and with that approach we want to generate executable systems from these language aggregates. The running example is as follows. Consider you have a robotic system that does your breakfast for you. And to do so, you have a software architecture running that controls two manipulators. One controls your toaster's lever, the other one controls the robotic arm to pick up and place toast. And your software architecture employs composed and atomic components, and on your left you see three sensors that have implementations written in Java. And for your controller, as you want to be able to reuse it with different programming languages, you have a model behavior implementation. And in this case, you have an automaton language. Can you see that from behind? Okay. I'm sorry, I didn't expect the room to be so big. Anyhow, this is a standalone language that is embedded in your architecture language. And you need a translation from that to Java as well, or whichever is your output language. For your ARM controller, your RobotArm expert has another favorite language that describes ARM movement in the joint space of the ARM. So you define positions, like toast down plate, the top two lines, and then you define programs over these positions. So it's a very high-level RobotArm programming language. And now you have the problem that you have a code generator that does generation from architectures with automata for you, but it does not take RobotArm programs into account. So from here on, you have two choices. You can either develop a new code generator, and you can do that by informal reuse, means copy and paste, and then duplicate your knowledge, your errors, and your maintenance effort. Or you extend it manually, and in the end, you will have a white box only approach where you have one code generator that catches all your behavior languages, and that won't be maintainable as well. So the problem here, and similar problem was debated in the first talk, is if you have n behavior languages, you have to do that n times. So either you have n different code generators, or you have one code generator for n languages, and the latter won't be maintainable. Our goal here is to generate general purpose programming language code for software architectures with dynamically embeddable, that means after deployment, embeddable behavior languages without modifying your existing code generators, so some form of black box composition. To tackle that, we had to tackle three questions. What is a code generator? It's a favorite question at our group because we have no answer. You could stick, for example, to IEEE, where a code generator is a piece of software that translates something to another thing. It doesn't help us. You have to define how the participating generators are selected, and you have to define how these are composed ultimately. And so far for the motivation and our contribution. Now we'll look into the actual generator composition, and we will answer all three questions. What is a generator? How are generators selected? And how are they composed in the next slides? And afterwards I'll show a video. And maybe it would be helpful for you to come a little closer because it uses small fonts as well. I'm sorry for that. So let's see. For our scenario, we have three generation concerns. The first being component structure, meaning components, ports, decomposition, etc. Component behavior, such as the automaton language or your RobotArm language, which we need to integrate, and data types. And from that, and only in this context, we can generalize it to three generator types we need somehow to integrate. Each of these types has certain properties we need for integration, such as specifying the input language. So each generator must exhibit which language it can process, like your automaton language or your RobotArm language. You need execution information. You need some form of generation context, meaning the information required by a code generator at runtime. And you also need to define product relations so you don't combine incompatible generators. If you realize these three types in form of interfaces, so now it gets a little bit more technical, you will define a code generator that's compositional, like this RobotArm to Java generator, based on some form of transformation artifacts that might be model to model or model to text, and the so-called generator description model. This model represents your code generator for composition. As such, it indicates which generator type via the interface it conforms to, so the represented generator. And it contains, for instance, which language your generator can process and how it is started and the constraints it imposes, etc. So to make that available to composition, we generate an implementation for it. So there are 2 generation steps until we have a generator aggregate, and in the first step, our toolchain processes these models, checks their well-formedness, and produces an implementation that is an actual Java class which realizes or implements this interface and contains all the information from the generator description model. After that, your generator is finished, and you can just plug it in. And given 4 generators, 1 for component structure, 2 for behavior, 1 for data types, you plug these into your application project using so-called application configuration models. Basically, that's a set of generator names. And the semantics is that given your software architecture and your handcrafted implementations, you will apply the generator selection made in the application configuration to the architecture. We have separated this from the architecture model because this allows us to extract the software architecture and use it with multiple application configurations. So what we, for instance, did is generate one software architecture to Java and to Python. So you reuse your models, and you need to specify only new handcrafted implementations for the components that are not modeled, so that rely on GPL implementations. So far, we have seen what a generator is for us, something that employs a generator description, and the generator selection is straightforward. It's 5 lines in that model, and basically only generator names and a reference to the architecture they are applied to. We now look into the composition mechanism, which employs the application configuration toolchain that again processes these models. It's a standalone modeling language, checks their well-formedness, and starts the generator orchestration. And the orchestration, the top row is generic to all our generators, and it directly interfaces the participating generators via their models. So we go through this step by step, and at first, of course, we check this application configuration. You could select generators, let's say 1 for component structure and 1 for automata, for a software architecture like the one I've pictured that employs another behavior language, and then you fail at this step. So there is actually multi-level language integration going on, and interpreting this application configuration means you have to look into your software architecture, you have to look what languages are employed, and look into the generator description models to see which generator capabilities are available. Once this has worked out, you start your component generator, and actually in this step you instantiate the behavior generator's description implementations. These are passed to your component generator, and this is a design decision that's due to the component generator being required to traverse a complete model AST anyhow. And once, as long as there are unfinished elements, component elements are processed by the component generator naturally, and unknown elements are tried to use with the behavior generator. So each of these behavior generators has this generator description model stating, I am a generator for automata, I am a generator for RobotArms. And looking up which language the behavior model belongs to allows you to match the corresponding generator. Afterwards, it produces a behavior artifact that is compatible to the product information, the runtime system I've managed earlier, and basically relies on conventions regarding the interfaces to be implemented. So given that, we now have seen what a generator is, how generators are selected, and how the orchestration is performed. And now we actually look into an existing generator. So we look into our RobotArm to Java generator project, and we will see that it's template driven. It employs FreeMarker as template language. We will see the generator description model and see how we employ Maven to actually produce an implementation that can then be used for composition. And I suppose you can't read it in the back. So I'm sorry. Still, there are a few seats in the front. Like that. Thanks. Okay. It gets even worse. I'm again very sorry. I have to press somewhere here. Oh, I hate it. Sorry. Finally. PowerPoint now has a very interesting feature regarding starting videos, and it's terrible. So what you see here is part of our template that actually produce Java code. The black line is Java, the rest are free marker directive. And these templates produce code that's compatible to your runtime system interfaces. Our generator description then identifies the start template, because we are template driven in this way for these generators. The language fragment it can process, so the behavior language, and the runtime system extends to compatible to it. Then we implementation, and basically that's amounts to running or tool processing Maven plugin. So that's the only thing you need to know besides managing your dependencies with Maven. And executing this toolchain is 2 clicks. Of course, again, Maven. So during execution, the models are passed, processed, the artifacts are compiled, packaged, and in the end, uploaded to our continuous integration server and to the Nexus, so you can just reuse these in your application projects. Now we see this implementation, we tend to implement the behavior generator interface. It contains the information from your generator model. So this is the only interface your generator has to the composition mechanisms. And it's a very small one. You have seen it has been 5 lines, I suppose, or 4. So very little knowledge you have to bring in. I've already mentioned this application configuration. Models you need to specify in your application project. Now we look into this ToasterBot application project. So if you want to look it up, there's a video on YouTube where we actually make it run. Here we just look into the project, and we will see that we have this application configuration model, which basically selects for generators the qualified names, the gray blobs from behind, and we will look into our component models. We will see the component behavior model. Again, we will employ Maven with a different tool, and we'll get a generated component implementation for the components with embedded behavior languages. So this may be execution actually performed to generate the composition. And again, there's not much to do for the application user. So you see a composed component model, and it's very simple. You have your source controller subcomponent, your controller subcomponent, and connectors. So this is the top level component. Now the controller, which has this behavior automaton, which is based on explicit. This is an embedding of a standalone language, and we can only do that because we employ a language workbench. And your RobotArm controller employs RobotArm programs, the provision the programs that are called drive home, pick up and deploy, and deliver to toaster. So application configuration model is quite simple. It just makes code generators. It can do more, but that's not part of this talk. And again, we have a project object model that runs our toolchain. So in this case, a different tool that takes care of processing applications and can read component models, etc. We're going to execute it. Again, we generate code, compile it, package it, deploy it to the Nexus. So all this is Maven-driven with the benefits that you can reuse it with your command line or different IDEs. It's not tied to Eclipse, although we like to use it. And now you see a generated class called ToasterBot that implements the interface of the runtime system, which is for the decomposed top-level component. This one has members for your subcomponents, and we'll look into these and how these employ delegation to interface the artifacts produced by the behavior generators. So actually now we have behavior implementation, this behavior implementation for automaton implements certain interface. This is where the artifacts are interact and realizes your transitions. So this is produced by your behavior generator, and that is produced by executing it from the component generator. We do the same for our RobotArm programs. You see again an interface, and here you have your position definitions that were part of your model. And afterwards you have a few auxiliary methods until you actually see the realization of the RobotArm program that were part of the model as well. So actually this is two-level integration. A, we integrate the code generator. B, we integrate the produced artifacts by convention to a runtime system. And the take-away message for us is it works. So black box generator composition for component connector ADLs works. That's good. It only works because we have built on a powerful language workbench, which enabled language integration and reasoning about models of different languages, such as application configuration and generator description and the software architecture with quite with ease. It relies on explicating your generator knowledge. So in many contexts, generators in model-driven engineering are second-level citizens. So you have great modeling languages, great integration, and then you just throw it at some generator and something happens. The point here is formalize your generator somehow. Make it more usable. Also, use Maven. Maven worked quite well for us. Also, Gradle and others would be doing too. And we can generalize this to other contexts where the number of different generator types is finite. So where we know which generators are available, what they have to do, how they have to interact. This does not work in different settings until now, and we currently look into generalizing this to different language integration settings. So thank you very much. The publications regarding this toolchain are available, and an Eclipse with built-in Maven, etc. is downloadable at the second link. Thank you.